Let me open our sessions and let me give the invite first speaker, Tomohiro Inagaki, Hiroshima University from Japan. We're all listening to you. Can you begin your talk? Do you hear me?
Thank you.
Professor Tomohiro, could you begin?
Yeah?
Yes, we listen to you.
Okay, thank you for the opportunity to make this presentation today. I talk about the inflationary expanding universe by complete scalar field. So the main part of this talk is based on the work collaboration with Sergei Orintov and Hiroki Sakamoto. And this is the outline of my talk. And I want to talk about, consider the gauge Nam-Yonarashino model to describe the complex scalar field. The main point of my talk is how to apply the model to the inflation era of our universe. Then I show some numerical results for the cosmic microwave background fluctuations. Okay. So, introducing my model, I will review inflation universe very briefly. The idea of inflation has been introduced to solve some cosmological problem. Why our universe is so flat, why the universe is homogeneous and isotropic, and no lyric abundance of any exotic particle is observed, and so on. So, the inflation is introduced to solve these kinds of problems. One of the evidence of the inflationary expansion has been observed in the cosmic microwave background, CMB. Inflationary expansion can be induced by the potential energy of so-called inflaton field. It immediately cools down the universe. After the end of inflation, the potential energy is released. So the universe is reheated again. Then the universe, after that, the universe cools down, and the proton catch the electron and combine the neutral hydrogen atom. After that, the photon propagates freely. We observe the photon as a cosmic microwave background. And it is considered that the fluctuation of the cosmic microwave background is originally generated by the quantum fluctuation of the inflaton field. So there is a possibility to test the model of inflaton from the thermal fluctuation of cosmic microwave background. In a slow-roll approximation, it can be described, thermal fluctuation can be described by the inflaton potential and its derivatives. So now we come to the main point of this talk. I introduce the gauge NZ Nam-Yonarashino model and regard the obtained effective potential as the inflaton potential here. So we consider the gauge theory with NS fermion flavors and assume that one of the gauge interaction, I write it G here, is strong enough to describe it by four-fermion interaction. So we start from this Lagrangian. It is called the gauge NZ model, and I consider it scale-up model of QCD-like theory, and we normalize the four-fermion coupling in this way for convenience. According to the auxiliary field method, the model can be rewritten by this Lagrangian. The auxiliary field sigma and pi indicates the composite scalar and pseudoscalar field. I note that the original Lagrangian JINR model can be reproduced by substituting these classical equation motions here. Please compare this Lagrangian with the Lagrangian for the gauge Higgs equal Lagrangian. Then you found these Lagrangians coincide if we drop the kinetic term and curvature interaction and positive coupling, and also normalize the Yukawa coupling Y and mass scale M square. So this Lagrangian coincides with the Lagrangian obtained from the gauge NZ model. It can be achieved by the Wilsonian renormalization group. To show the equivalence, it is more convenient to transform the field in the gauge Higgs or Lagrangian in this way. Then we get this form of Lagrangian, and we solve the renormalization group equation. Then it has been found the solution of renormalization group equation to satisfy these conditions. Under these conditions, you can see this term disappears. So it means that the gauge Higgs Yukawa model coincides with the gauge NZ model at the completeness scale lambda introduced here. This is the schematic image of my assumption. The gauge NZ model can be described by gauge Higgs Yukawa model with completeness conditions. I assume that the model dominates the energy density of our universe at the inflation expansion era and adapts the chaotic inflation scenario of this model. Okay? I also impose the following assumptions. We neglect the learning of the SN gauge coupling, and we consider the completeness scale is large enough and take the lambda infinity limit. We keep time up to linear in term in R and drop higher order term in R. We also assume that only the field sigma contributes the inflationary expansion here. Then we get the renormalization group improved effective potential. Parameters of the model are the constant gauge coupling alpha, for fermion coupling G4, and the number of fermion flavor NF. NC is the color of SU NC, and the renormalization scale mu here. We have 5 parameters in this model. I use this potential to calculate the CMB fluctuation numerically. We employ the slow roll scenario. I have no time today, so I can only show some keywords. Please see our paper for details. The CMB fluctuation can be evaluated in the following way. First, we define the metric tensor of the frame in so-called the Einstein frame. Then the exit end of the information is found by evaluating the so-called slow roll parameter. Epsilon and eta is order unity. The value of the field sigma, initial value of the field sigma is fixed to generate a suitable E-folding number. It is necessary to solve the horizon problem. Then we calculate the density fluctuation, spectral index of fluctuation, the ratio between the tensor and scalar type fluctuations, and the running of the spectral index. So, as I said before, the models have 5 parameters. These parameters, we evaluate the CMB fluctuations as these parameters vary. I note that the mass scale is normalized by the Planck scale. First, I show the typical behavior of the effective potential. If we consider case NF times NC is larger than 24 pi square or NZ limit, the potential has such kind of the behavior. We are local maximum observed. In this case, we need to fine-tune the initial value of sigma near the maximum. So, to avoid the fine-tuning problem, we consider only the case NF times NC is smaller than 24 pi square here. In this case, we found the slope of the potential decreasing as the gauge coupling alpha decreasing. It means that the smaller gauge coupling generates a smaller fluctuation, so we can tune the amplitude of the density fluctuation by the gauge coupling alpha. So we numerically evaluate the density amplitude of the density fluctuation delta. It should be order 10 to minus 5th from the observation. So if we take the alpha is order 10 to minus 12th, delta is almost 10 to minus 5th. So we fix the gauge coupling alpha at the order 10 to minus 12th to reproduce the observed amplitude of the density fluctuation. Next, we consider the dependence of four-fermion coupling and energy scale mu. In this table, we show the amplitude of the fluctuation, delta, and the spectral index NS and tensor to scalar ratio R, and also the running of the spectral index alpha S. And here I only notice that all the results are consistent with the observed data observation Planck 2015. Here we vary the renormalization scale and the four-fermion coupling. All the value is almost fixed. And today I have no time to show the NC and NF dependence, but these parameters also have no large contribution for in the case NF time NC is smaller than 24 pi square. Now I come to the conclusion. Today I applied the composite scalar model to the inflationary expanding universe, which shows the numerical results for the CMB fluctuations under the slow roll and the other approximations. Then we found that the gauge coupling alpha should be the order 10 to minus 12 to generate a suitable density fluctuation. We obtain a consistent spectral index tensor to scale ratio running of the spectral index with the Planck 2015 data. The validity of some approximation considered here is not so clear, so we should consider the lower complexity scale. In this case, we observe larger parameter dependence. We show some result in the abstract. And the scale-up model of the QC-like theory, there are many meson and barium-like composite fields. So it may be interesting to consider the multi-field model of information in this model, and we should introduce some standard model field and discuss the reheating and preheating error. And it is also interesting to extend the model with some dark matter candidates. Thank you.
Thank you very much, Professor Takhamira, for your very interesting talk. And I want to ask, have any questions for Professor Takhamira? Yes.
I have question. Dr. Takhamira, when you said about density, what order of density you consider it? Which density you consider it? For example, it could be density for quark-gluon plasma.
You mean the density of the infraton field here?
What? I'm asking about scale of density. What density you consider it?
It's much larger than the quark-gluon plasma. The typical scale of information is 10 to around the Planck scale.
Thank you.
Yeah, so much larger than the quark-gluon plasma we consider here. So I say it's the scale-up model of QCD light theory.
Thank you. So I have one question too. In the slide 7 or 8, you talk about the low energy and high energy. What do you mean when you talk about low energy in the figure? What do you mean?
Okay.
Yes. Next slide. What? Low energy and high energy. What do you mean? Yes.
High energy means the beginning of the universe. I mean, low energy is it's near the beginning of the universe. Then inflationary expansion occur around here. Then reheating and decombination occurs, and now we are much low energy scale, between the low energy scale.
But in scale, it's how many is energy? What is in scale? In figure, how many energy? In GeV, in scale, yes. In scale of energy, yes.
Yes, high energy means almost the Planck scale.
Okay.
Planck scale. And because of the inflation, low energy, it is also the high energy compared with the usual QCD scale. And usually we consider the heating energy temperature is almost 10 to 11 GeV. So low energy is also very high.
Yes, thank you very much. Do you have any questions? Okay, next.
I have one question. So, is it possible? So I would ask. So, is it? Okay. So about cosmological constant. Cosmological constant is same as in usual inflation theory, or it depends on the density or some other parameters.
About the cosmological constant.
Yeah.
Does it expansion by the potential energy of the complete scalar field? So I don't introduce the cosmological constant here. Any cosmological constant.
Okay.
So the cosmological constant is energy induced inflation expansion.
Okay. Okay, thank you.
Thank you very much for your answer, and we're proud that you take part in our conference. Thank you. Okay, next talk. Askerov, ne diyor? Please, next please. Abi yazılmıyor Pakistan Askerzade. İman Askerzade, Ankara Üniversitesi, Türkiye. From
My talk deals with dynamical properties of small Josephson junctions. Next, this one. As you know, in small Josephson junctions, there are similarity with condensed matter theory, especially for the case of periodic potential, because of Josephson junction means that there are periodic potential cosinus phi, and for these junctions, in the case of when Coulomb energy in Josephson junction is at the level of and higher than Josephson energy, there are such energetic pictures, and here in horizontal line we have similar to condensed matter theory, quasi-charge. Quasi-charge, it means Q over 2E. 2E, it means charge of Cooper pairs. And in general case, next one. In general case, Josephson junction is characterized by the parameter kappa. Parameter kappa, this one is ratio of Josephson energy to Coulomb energy. Josephson energy, this one, amplitude of Josephson potential, this one 1 minus cosinus phi. Phi, it means Josephson phase. And here we have Coulomb energy. And as shown by investigations many years ago, this one 15 years, and it was related with preparation of small size Josephson junctions, submicron Josephson junctions, and when we have Josephson junctions with electrical capacity at the level of femtofarad, when is lowering its capacity, this Coulomb energy is grow, and when Coulomb energy is grow and higher than Josephson energy, in this case we have Coulomb blockade effects. Coulomb blockade, it means that in such small Josephson junctions, transfer of Cooper pairs from one electrode to another is similar to dropping effects. And for the describing of these effects, similar to condensed matter theory to solid state physics, here we can introduce block capacitance which related with quasi-charge. It means this one similar to effective mass in solid state physics, and it can be negative. Next one. And in general case, you can see here schematic show of Josephson junction in this case, and in this case we have variable related with quasi-charge, and here is through such equivalent scheme of Josephson junction, and our aim to take into account these effects in the case of Josephson junction based comparators. What it means comparators? Next one. Next one, please. Josephson comparator, it means that in the case of superconductivity electronics is the basic elements of Josephson based computers, because of as shown by investigation Likrif in Stony Brook University, in superconductivity electronics we can reach level of 770 gigahertz of computing frequency. This one very high than in the case of semiconductor technology. But in the case of superconductor technology, there are a problem with technological problem, reproducibility effects, and there are another problems with lowering of size of Josephson junctions. We should take into account column blockade effects. Here I schematically show balance comparator on small Josephson junctions. This one first Josephson junction, second Josephson junction. From here, generator of strobe pulses, and strobe pulses in general case can be considered as triangle pulses. And from here come signal which we should measure the form of signal. And here equivalent scheme of Josephson junctions with small Josephson junctions, and as you can see, Josephson junction can be considered as nonlinear capacitance and nonlinear inductance. Up to now, in our investigation, we take into account only this term, and block conductance was not taken into account, and it is clear that inclusion inductive terms seems interesting from the point of study dynamical properties of Josephson systems and Josephson comparator. Next one. And as shown by Zorin investigations in feasibility letters in 206 years, block inductance in general case can be approximated by the mathematical formulas, and near Q equal is here. This one close to Brilliant zone. We can approximate this block inductance in such a here phi 0 is the quantum of magnetic flux. EC, this one critical current or Josephson junction, and kappa ratio parameter. This one ratio of Josephson energy to Coulomb energy. Next one. And for the study dynamics of such system, we write here system of nonlinear differential equation. As you can see here, we have inductive term because of in our early study we take only these two simple terms, first derivative and here nonlinear function. But here we include this one, first term, which related with inductive effects in small Josephson junctions. And here there are periodic function. This one periodic function can be obtained from the foundation of spectrum of electrons in periodic potential, Josephson potential, and here Q is a quasi-charge, similar to quasi-momentum in condensed matter theory. Next one. And here is a case of small signal and taking into account linear growing sampling signal because we have measurable signal, and there are pulse signal for the measurement. And here we can get any equations for study of dynamics, and here we have presented analytical solution. This one first stage related with linear condensators, linear capacitance, and in this case we have linear charging of condensators. Second and third stage is related with changing of voltage in Josephson junction. Here we have delay times. This one related with nonlinear character of growing of current in Johnson junction, and this one delay time related with velocity of growing. This one sampling rate of voltage across junction, and here phi0 is a flux momentum, flux quantum, and another notation. This one EC, critical current. And using this analytical solution, we present the transfer characteristic of such comparator. It means that when we use as input signal a Heaviside function, and here we have similar oscillation, and for the estimation useful dynamical properties of Johnson junction, it is useful to determination of time resolution. What it means, time resolution, is this one. Time resolution is the time between at the level 0.1 and 0.9, and using our notation here we have analytical expression for the delay time, and using this expression after determination of these levels 1 and 0, 0 and 9, we have next one please. Next one please. Next. Here we have analytical expression for the time resolution of balanced comparators on small Johnson junction, which take into account mesoscopic tropic effects in Johnson junction. This one 1 and 15, and here we have this one parameters which related technological method preparation of Johnson junction, and here K parameters, and here we have also any estimations for the influence of column blockade effects. We must take into account kappa parameter should be 1/3, and taking into account critical current of such small Johnson junctions at the level microamperes, that's 0.1 microampere, and we have after estimation we have result 15 picoseconds, 0.15 picoseconds. This one means that in principle this one is good result, but here we should take into account that these effects are related with kappa parameter. Kappa parameter is the ratio of Johnson energy to Coulomb energy. With lowering of Coulomb energy, K is grow, and when K is grow, time is also becomes time resolution of such comparator is better than in the case Johnson junction. But here we have any discussion related with realization of similar effects because of high TC superconductors. For example, this one, this one, BISCO-based superconductors, BISCO materials. This one, high TC superconductors, is layered system with Josephson interaction between layers. If you take similar monocrystals and we have make small size Josephson junctions, and using this one BISCO nanocrystals, we can tuning parameter kappa, and because we can change this one relation geometrical size of such Josephson junctions, and as a result we can tuning this parameter kappa. And tuning this parameter kappa, we can changing the time resolution of balanced comparators, and it means that in principle in future we can prepare good Josephson schemes related with good time resolution. Because of increasing of time resolution, this one is good parameter, and this one can be new technological achievement because of general problem in Josephson junction electronics related with reproducible character. Because of when preparing of Josephson tunnel junctions, there are big problems in preparation of, for example, to do Josephson junctions, maybe integral schemes with chips with 1,000 Josephson junctions with the same parameters. But in the case of BISCO superconductors, preparation of these Josephson junctions can be easily, and the problem can be solved. Next one. And as conclusion, we can say that in this short communication we presented the result of the study. Josephson balance comparators with comb effects because of, as I say, in such dimensions, in such Josephson junctions, there are effects of column blockade. It means that transfer of Cooper pair from one electrode to another electrode is similar to dropping, is water dropping. It means that firstly transferred one Cooper pair and second Cooper pair, and situation is different from the classical Josephson junction. In the case classical Josephson junction, no restriction for the tunneling of Cooper pair from one electrode to another electrode, because of, in the case, for example, and in the case of normal conductors, in section of conductor, or maybe another structure, no problem of tunneling electrons. But in mesoscopic systems, in small systems, there are column blockade, and the column blockade, it means that electrons going tunneling column blockade case. One electron, one Cooper pair, second Cooper pair, and such. And here we present analytical theory for the estimation of such effects. Thank you for attention.
Thank you for your talk. Do you have any question in online? Okay, I have one question. Do you have your estimation for your formula to apply applications?
Application.
Oui, practical application. Do you have it?
In our case, here I also only present the result of, in principle, there are experiments in which column blockade effects reveals on experiment, but experimental realization of spatially balanced comparator, but what it means balanced comparator, two Josephson junctions, come here drop pulses, and here measured with signal. The signal is applied in parallel to parallel, because of, in this case, fluctuation is excluded from the system. Okay. In one Josephson junction, there are experimental data related with column blockade, and this realization and measurement of ID characteristics, and another problems when in applying the external magnetic field, because of when we apply the external magnetic field, Josephson effect is lifted because of external magnetic field is destroyed. Superconductivity. When superconductivity is destroyed, no Cooper pairs and no tunneling. But in this case, we investigate property of balance comparator, balance between two junctions. Similar studies is not, but this one first theoretical estimation, and I also have presented any discussion related to what we can experiment and realize this one. This one we can experiment and realize using, for example, BISCO-based high-tissue superconductors. Because of BISCO-based high-tissue superconductors is natural Josephson stack. And relation between planes is Josephson characters.
Thank you as well for interesting talk. Thank you. And we're glad to our conference connect to Pavel Asatyani. Do you hear us? Professor Asatyani from Georgia. Do you hear us? Pavle? Do you hear? Could you begin your talk? Pavel? Okay, I think Pavel now is beginning to. So we pass these speakers and maybe to connect to our meetings a few minutes. Okay, we invite to next speaker. Okay, Pavel, we don't hear you. Are you hear us? Pavel, we can see your slide, but we don't hear you. Do you hear us? Could you tell something? Will you turn off your microphone? No? We don't hear you, Pavel. Ну, я читаю вот. Окей? Okay, we're waiting you. No, sorry, we don't hear you again. I think you have a problem with your microphone. Okay, I suggest we go to next speakers and you, Pavla, have it several minutes to prepare to the next talk. Okay, I invite to the next speakers, Professor Mai Suleiman from Pakistan. You are welcome. Could you begin your talk?
Yes, 1 minute.
Okay. We're glad to hear you and wait until you upload your talk.
Yes.
Is Pavle? Okay, sorry, Pavel is okay, could you begin? We hear you, but I'm very, very bad. Павле? Окей, тогда мы идем к Майке, да? Okay, sorry. We couldn't connect to the Pavle and we go to the Professor Mais from Pakistan and suggest to begin your talk. We're ready to your talk.
Okay, thank you very much. Good afternoon, everybody. First, I would like to congratulate the jubilee and to wish all the best to it. And then I would
Thanks
like
a lot.
to thank the organizing committee for the invitation and special thanks to Professor Rauf Jafarov. Thank you very much. My talk is named Could Quark-Coryon Plasma be a source of super high energy cosmic rays? As you understand, the talk will focus on a possible source of a super high energy cosmic rays. When I say super high energy cosmic rays, I mean particles with energy with greater than 10 over the 15 electron volt and more. I think that maybe such type particles could be produced in hot and dense quark matter, maybe in quark gluon plasma. So we consider that maybe quark gluon plasma could be a source of super high energy particles. As we know, the cosmic rays is a main component of our universe. We believe that actually cosmic rays can solve a very important information about the creation and evaluation of our universe. But as I said, up to now, we don't know exact source of particles with energy 10 over the 15 electron volt. Even people don't know if these particles produced in our galaxy or come from some extra galaxy. That's why today this problem is open problem. And as you know, first time cosmic rays was observed in 1912. And in 1935, first time, physics could detect a extensive air shower. And in 1948, first time, people can detect a main component of cosmic particles, cosmic rays. That was mainly protons, some helium nuclei, and a few heavy nuclei. In this figure, you can see a flash of cosmic rays as a function of their energy. Here you can see three areas. First area, yellow area, this particle, this cosmic rays connected with solar, mainly is as a solar cosmic rays, because they are connected with sun and main source is the sun. Their energy could be maximum up to 10 over the 10 electron volt. And we think that today we know a lot of things about these particles. But next area, second area, 10 to 10 over the 15 electron volt. And today we think that these particles, cosmic particles, produced in our galaxy. That's why we say that that's galaxy cosmic rays. And last area where energy greater than 10 over the 15 electron volt. But this area is an unknown area. That's why people say that these particles may be extragalactic particles. Why? Because to high energy cosmic rays with energy 10 to 15 GeV could be produced using some huge magnetic fields in our galaxy, which created by some massive stars. For example, by pulsars. Pulsars could create a huge magnetic field, and this magnetic field could accelerate particles. But theoretical calculation demonstrates that maximum energy of this source, this cosmic rays, could be only 10 over the 15 electron volt. It means other particles which has energy greater than 10 over the 15 electron volt, their source unknown. Today I would like to discuss here some possible source of these particles in our galaxy. It means we are looking for some source without acceleration of the particles. And now I am going to my area, heavy ion physics. And what I would like to say you that first experimental result coming from a relativistic heavy ion collider from Brookhaven National Laboratory demonstrate that they could create a hot and dense matter. But this hot and dense matter has some, for this matter, people can observe a V2. It means electric flow. It means there are some asymmetry. You can see this thing in this picture. There are some asymmetry in system. It means, and here you can see this asymmetry increased with transfer momentum, and main thing that this behavior can describe by hydrodynamics model well. What does it mean? It means that actually what hot and dense matter created by Rig is not ideal gas. It is not gas. It has some correlation. It means it has to be something like, they start to say that it is something like a perfect liquid. And moreover, as we know, first experimental result coming from Large Hadron Collider, they studied V2 as a function PT in lead-lead interaction at energy of the Large Hadron Collider. And they observed it again V2, and that V2, so it means elliptic flow increased with PT. Moreover, Large Hadron Collider with Alice detector can merit a values of V2 and demonstrate that elliptic flow increase with energy. It means matter became hotter and hotter, and correlation also increased. What main result of this experiment is that in a newly created hot and dense matter, we have some collective behavior in level of parton. It means parton strongly correlated inside of quark-gluon plasma. What we try to use this result. We try to this result that this collective behavior can lead to formation of some system, coherent system of quarks and partons. It means QGP can have some structure inside QGP, something like color glass condensate could be appearing due to, for example, percolation of partons, and also grown a number of gluons as a result of interaction. So if we have any such type formation inside quark-gluon plasma, so interaction with this object, as a result of interaction with this object, other partons could get a huge transfer momentum. It is like inverse Compton effect. So it means these particles could be accelerated inside quark-gluon plasma. It could be very interesting, and maybe it could be considered as some source of quark, as some source in future of cosmic rays. Why? Because as we know, as a result of collapse, for example, supernova, as you know, it is most massive particles in our universe. Two very interesting objects could be appeared. One object is neutron star, other object is quark star. Both of them has a huge density, and theoretical calculation demonstrates that in the center of this object, matter could be in state of quark-gluon plasma. And today we have a lot of reasonable experimental that really neutron stars exist. We are sure that we have a very clean experimental result, but unfortunately, up to now, we don't have any clean signal about existing of quark star. With quark star, this effect will be more clean, more easy. But in any case, if in universe we have object which contain quark gluon plasma, so as I say, due to collective behavior in this medium, some object could be appeared, and interaction with this object could give other partons high energy. And main thing that energy in this case of partons could be limited only with parameters of this system. Only with parameters this system. And that's why if for example, number of particles in this system will increase and increase, it means the final energy, transfer energy also could be increased. And this energy could be calculated using, for example, coherent tube models and etc. So what I would like to say that last experimental results coming from Large Hadron Collider, also from RIG, demonstrate that there have to exist collective behavior for partons inside quark gluon plasma. And this collective behavior can lead to formation some group, some system of partons. And as a result of interaction with this system, quarks, partons could get a very, very high transfer momentum. And it means, but in other hand, we think that such type object could exist also in our universe, in the center of neutron and quark stars. And maybe they could be also source of super high energy cosmic rays. Thank you very much.
Online. Professor Süleymanov, I have one question, maybe it's native questions, but when we talk about the quark gluon plasma, we talk about the free quark or in some state of the quark?
No, it means a confined matter. Confined matter in some volume, and this volume have to have size of hadrons.
Okay, and as I know, in Alice, next day begins the new run for in ion beams.
Yes.
You are waiting new run, yes?
In September, November, they have a run.
Okay. Thank you very much. It was very interesting talk. And we go to the next speaker. Pavel, do you hear us?
I hear you.
Okay, nice. Could you begin?
Can I speak?
Yes, you can speak. You can begin. We are listening to you.
Thank you. Results of my report are based especially on history of physics and technology, discovery of superconductivity and helium superfluidity in experiments of Camerlingones and Kapitsa, awarded with Nobel Prizes, have led us to the formation of macroscopic quantum physics of condensed matter and postulation of macroscopic wave function of Bose-Einstein condensate of ideal gas in the works of well-known for you, London, Richard Feynman, Bardeen Cooper Schrieffer, leading to quantized vortexes based on the below-mentioned circulation, where f is the amplitude of wave function, L vector, p phase of wave function's real part in the radius vector. Due to these works, appearance in quantum metrology, fundamental constant as a above-mentioned circulation is established experimentally, well known for you by Bynon and Josephson. In such a way, the indicated relic factor of helium in the universe formation from the very beginning is of great historical and practical interest. The fundamental condition, next one please, the fundamental condition of the circulation quantification has been obtained as follows, where L is a contour of the circulation, where S, velocity of superfluid motion, M, mass of helium atom, E, charge of electron, A is Maxwell vector potential, H, Planck's constant, and order of quantification. Dear colleagues, generalization of experimental equations of quantum hydrodynamics of superfluids and Cauchy circulation integrals in first expression has led us to indivisible two-dimensional phenomenon of motion, the circulation of phase angular wave vector, real part of wave function, part of the circulation of the condensate using Feynman theory, where nabla phi is the boundless phase velocity of superfluidity, limited due to our feelings organs, possibilities, boundaries only. See below, neuron in figure 4 with embedded circulation. I would show in the following view. The differential L, differential of coherence correlation length in the space of generalized coordinates PL. Defining motion as the Bohr complementarity of oppositions, the charge and coherence correlation the same, we have come to the universal kind of motion as the indivisible change of phase in its coherence, giving circulation of matter, and to the Planck's constant as the derivative of more fundamental value of circulation than the elementary action quantum following the relation. Of course, conservating all the richness of the Planck physics, the history of physics followed us to post-Planckian physics. As is known, Einstein is known well for us. Einstein has built his theory of relativity on the basis of the space curvature tensor using the Maxwell electrodynamics of continuous media. As a result, we have come to conclusion that the space curvature itself is the derivative of the universal circulation. As a result, the charge and mass are the derivatives of the same space-time curvature tensor, revealing the same nature and carrying only the function of bond coefficients between Planck's constant, action quantum, and circulation in our first expression. Circulation generates itself the united space-time. So, space and time are indivisible as derivatives of the same nature circulation in our model throughout, of course, only throughout history of physics. Being engaged in history of science and technology, our analysis of the whole history of science shows the universal character of circulation, which is in the basics of all fundamental physical experiments and observations, beginning with the very first lines of the Old Testament of the universe creation. And the God soul carrying on the waters with the circulation of the hydrodynamic orbits closed on the God soul. Circulation itself, in its classical definition at the same time, is a vector of point moving on the orbits. See figure 4D in my report. As a result of the above-mentioned experimental facts and postulates, the boundary between quantum and classical physics, defined with the Heisenberg principle of uncertainties, is being cancelled, and we have come to the classical physics on the new level of universal motion, as the non-quantized classical circulation, with discreteness. After all, conserving, I should like to repeat, conserving all the richness of the very productive Planckian physics. Following the informatology, the second one, science and information nature studying, approved with the special United Nations doctrine of informatological development of the mankind in 21st century, we have defined accordingly the information is a system of relations, lying in the basis of all kinds of correlations in the nature. And information in the language of circulation throughout this doctrine has got the fundamental definition throughout Bohr Heisenberg complementarity of uncertainties as the united correlation of oppositions. What oppositions? Phase wave vector changes and their coherence in the circulation, leading us to the two-dimensional universe and lying in the basis of all kinds of interactions, being defined through phase shifts in their correlations. As soon as we try to fix separately phase change or its coherence, we have come to uncertainty, as far as you know that. Fundamental sense of Heisenberg principle based on the Bohr complementarity. As far as you know well, now we have through Scientific American and CERN works, there is a crisis in physics. So I mean that our results throughout history of science give us opportunity to overcome this crisis. This report was reported at the Europarlament and physicists of Europarlament, and is protected and at Nobel Symposium Committee. As a result of above mentioned all matter particles from Cooper pairs, electron hole pairs, up to Higgs bosons can be represented as of the same nature coherent de Broglie wave packages of circulations throughout positive and negative oriented Kepler-Bohr stationary orbit superpositions, and revealed also in the well-known for you Hudson's two-dimensional functions unity of maximal likelihood of mathematical expectation and dispersion of the random values of wave vectors. Vector whose all directions are equiprobably coincided with traveling wave direction generating scalar Bose-Einstein condensate. Generalized in the geometry spaces of vertices from Democritus, Descartes, Newton, up to neurons computing, united on the same basis of the circulation in our model. See figure 4a. So, instead of unsuccessful searching of elementary particles, we have come to fundamental elementary physical phenomena as a circulation forming our universe. Having repealed from Newton's method of fluxes and Minkowski geometry of numbers, with his fundamental tendency of algebraic curves, finally noted, as you know well, by Gilbert and Weyl, in their introduction to space and time by Minkowski, astonishingly have coincided with Euler's approach in his analysis of infinitesimal introduction. All these signs of the language, including zero and infinity signs, are constructed in our model as a geometrical patterns of derivatives of curves, tangency, in the circulation with opposite signs, following physics of Landau-Rotons, defined by Landau as a soul of disappeared vertex, is well known for you. On the basis of above mentioned, we have come to conclusions that whole history of physics throughout quantized vertices, circular motions, or spins generating matter is based on the circulation of phase wave vector wave function as a new language fundamentals, generalized finally in the theories of superconductivity and superfluidity by Onsager-Feynman and Bardeen-Cooper-Schrieffer, experimentally improved accordingly in Winant's and Jefferson's experiments, which showed earlier, awarded with Nobel Prizes. Earlier, we have constructed the computer machine as the field most metal oxide semiconductor transistor with circulation ring geometry, tested successfully on the cosmic apparatus, revealing the negative transversal resistor of tunneling phase transition between normal matter, visual, and unconscious superfluid, superconducting spiritual states according to the two-fluid model of supraconductivity, suprafluidity of some semiconductors. This superfluid state experimentally correlated with 5-7% of the above-mentioned Bose-Einstein condensate, discoveries awarded with Nobel Prize, as you know well, in our opinion, is the limit state only of experimentally interpreted part of the universe, so-called black matter, due to the above-mentioned natural narrow computing limited possibilities. As a result, we have come to the basics of universal mechanism of our geometrodynamics language on the wave vector circulation put in the very nature of neuron. See figure 4, model of neurons with superconducting axial and radial ion currents of the circulation as the universal machine. Using the circulation as fundamentals of universal language, we have transferred the circulation in the machine language of information technology too. Following our above-mentioned Morse field transistors with circulation ring geometry, last investigations in nanotechnology show for today the revealed opportunity for construction of the spin transport and the Internet machine on the basis of circulation, taking into account that the spin itself is the derivative of the circulation. As a result of last investigations in nanotechnology for today, the fundamental type of machines remains above mentioned Morse field transistors with circulation ring geometry. So, we have got for today the model of machine with universal computing language, including circulation, which communicate two natures, micro in its ideal superfluid and normal components in the two-fluid model of superfluids, uniting visible and invisible parts of our universe with the feedback. Materials, as far as I said, have been constructed at Nobel Symposium. Thank you. Thank you. Thank you.
Thank you very much for your interesting talk. And I want to say, do you have any questions from your online? Okay, do you have a question from the room? Yes, we have one question.
Thank you.
I would like to ask you about influence of what is the relation between superconductivity and Minkowski space? Because of in our consideration of superconductivity, normal superconductivity, and can this matter superconductivity? No effects related with Minkowski space and any theoretical model describing of superconductivity in Minkowski space is very
thank you.
rich for me.
Minkowski geometry gave us possibility to construct every language sign on the geometrical circulation. Any sign of language may be constructed is a superposition of prove Nobel complementarity principle.
Okay, thank you for the answer, and we're all time we're waiting, we're tight, and so we go to the next speaker. And I want to say I'm sorry for breaking during our conference, and go to the Professor Jafar Frau from Baku State University. You are welcome. Can you begin your... Okay.
I would like to discuss some properties about the number generalizing model and analog next leading order contribution to quark mass in finance sector and some other properties. Okay, which related with regularization procedure in number generalizing models. Okay. Next. The report is organized as follows. In first section, we describe the method of construction of midfield expansion with the fermion bilocal. Okay. So for the number generalizing model with SU2 vector axial symmetric for quark interaction, and for the sake of completeness, consider the well-known leading approximation result of this model. In section 2, in comparison to discuss the calculation in dimensionally analytical regularization and four-dimensional cutoff regularization span, we show that four-dimensional cutoff, the Nazim contributions can destabilize the NGL model. In section 3, the analog correction to quark mass, which in pi amplitude sector gives us the symmetrical result. The corrections in both regularization in four-dimensional and dimensional regularization equal strongly to 0. Next. The Lagrangian is the usual form. Schwinger-Dyson equation also is the usual form. Next. Genetic functional has also the usual forms. Okay. First, general leading, general order functional, generative functional has the form which gives us the following equation. Next. The leading approximation generates the linear iteration span. Consists is a step-by-step solution of the equations as the form of Schwinger-Dyson equations. Okay, next. Functional Gn is has the form where Pn is the polynomial of 2n degree on the bilocal source. The unit connected green function of the leading approximation is the quark propagator, where m is dynamical quark mass, which is a solution of the Kapf equation of the NGL model in the chiral limit. Okay, next. The first iteration step contains the leading order equation for the two-particle quark function, where K is the kernel of this integral equation. The graphical form for this two-particle function for the amplitude has following form, which includes only the propagator of the quark. And first order quark function equation has the following graphical form, which in homogeneous term contain two quark main leading order function. Okay, next. Since the number generalizing model is the near-field approximation includes quark loops, the essential aspect of application of this model is the regularization. Most common regularization in number generalizing model traditionally entail a four-dimensional cutoff in Euclidean momenta or three-dimensional momentum cutoff. Other regularization, Pauli-Villers regularization, and non-local Gauss form factors also use it in number generalizing model. The least common regularization for in-gel model was a dimensional regularization. Okay, next. But next, it should be stressed that the treatment of dimensional regularization, the regularization parameter is not all of deviation in the physical dimension of space. In best report by Professor Tomohiro Inagaki in conference celebrated the 70th anniversary of Georgian National Academy of Sciences in 2011 year, and also the collaboration with Professor Alexander Kvinikhidze and other scientists about the characteristic features of the number generalizing type 4 fermion interaction model in the dimensional regularization has been in detail enough discussed. Okay, next. However, okay, next. The model parameters in our approximation in leading order Kira condensate, quark mass regularization parameter C, and dimensionless Kaufman K has the following form. Okay, next. It is, but in four-dimensional cutoff regularization also were calculated the model parameters. As it's seen from these tables, the value of the main parameter, quark mass M, in the model with four-dimensional cutoff is much more sensitive to the value of the chiral condensate in comparison with that of the model of dimensionally analytical regularization. Okay, next. First order equation of mean field expansion define correction to quark propagator. This equation has the form. Next. Okay. We'll discuss it, all solution of this equation in Russian Journal of Physics in my previous works. Please, next. Science. This calculation, numerical calculation, gives us since a pi correction to quark mass in both studies, that in both regularization equals 0, this value are full correction to quark mass. Regularization and four-dimensional cutoff regularization. Okay, next. Okay. Here, using the leading singularity approximation, we have the following ratio for the quark mass in next expression according to this expression. The pi contribution in quark mass is equal 0 according to this formula. and this formula. Okay. In both regularization, it is properties of the our approximation. Next. In my opinion, this result related with result which by academician Alberto Felice and all in this book, which it is more likely connected, recurrent imposing that all mass correction to the sum were equal to 0. It is indemnification follows from invariance of transformation concerning gamma 5 group transformations. Okay, next. Next. It is originally investigated. Okay, next. The condensate and the quark mass correction allow us to specify parameter of SU2 in GL model. We modify formula for condensate as follows. The formula Phi stays the same size correction to amplitude generated in the next order of mean field expansion. The quark mass is the mass. Following values of model parameters for this improved choice are given in tables 3 and 4. Please, from Russian Journal of Physics. In dimensional regularization, is it period? Next. For dimensional analytical regularization, we can estimate all parameters for physical values for condensate but next. There is very important moment. For dimensional cutoff, the meson contribution can destabilize the non-Euler model. Okay, note that increasing a number of flowers is at UN F non-Euler model, the situation takes a turn for the worse because a main pseudoscalar contribution is proportional to NF. As that, for dimensional analytical regularization, the situation is principally different due to the coincidence of sign of meson contribution with the sign of leading contribution in condensate. For this regularization and stabilization of the model take place. It is clearly seen values for regularization parameter C increase in comparison with the corresponding leader order values. Is a shift to a region of stability of model where this meson contribution decrease. The original result was published in Russian Journal of Physics, my earlier works. Okay, next. Thank you
very much for your very interesting talk. And I want to ask, we have some questions from online. Please. Just we don't hear you. Could you repeat, s'il vous plaît? Repeat your questions, please.
Yes. You evaluate the stability of the loop expansion in NZL model using the 4-dimensional cutoff regularization.
Yes, okay. It is 4-dimensional version, but the originally works.
Yes. My question, it is the stability is a property only for observed in 4-dimensional cutoff regularization. I mean, 3-dimensional cutoff regularization, such kind of stability cannot be observed.
I would like to discuss this question in detail for you after the session in my email. Moment. Okay. Thank you, Tomo, for your question.
Okay, thank you all for being part of our conference. And I want to say sorry for our not planned breaking our conference is connected with technical problems. And I want to close our sessions today and hope we meet next year in this conference. I want to say thank you and to all. Bye-bye.
See you later.
See you later.
See you in Baku.
See you.
Next meeting.
Next meeting.
Also. Thank you very much.
Thank you very much.
Bye-bye.
Bye-bye.